In this section, we're going to look at systems of linear equations in two variables. Now, to begin, let's look at a nice GeoGebra application that can help us visualize what's going on with the system of linear equations. The way to think about a system of linear equations is that you've got two lines graphed on the same plane. So here we can see my line in blue and my line in red. The line in blue has a slope right now of 1.2 and an initial value of 1. The red line has a slope of 1.8 and an initial value of negative 0.6. And whenever we're looking at a system of linear equations, we're asking ourselves, where do they intersect? So for instance, in this problem, they intersect right here. Now, whenever we've got two lines graphed in the same axis, there's going to be three options. One option is that they'll intersect in exactly one place. The second option is that they will never intersect, and whenever they never intersect, that would have to be whenever they're parallel lines, which means their slopes are equal. Now, when lines are parallel, that means when they're written in y equals mx plus b form, the constant that's getting multiplied by the x is their slope, and here we see the slopes are the same. So for a line whose slopes are the same, they will never intersect for any x value. So this is whenever you would have no solutions. So we've seen they could intersect once, they could never intersect, and then the final option is that they could intersect at actually all points of the line, which would be the case when they're actually the same line. So if they had the same initial value and the same slope, when we graph them on the same axis, they overlap each other perfectly. So here, there's infinitely many solutions because every point on the line is a solution because that's a point of intersection. So let's just keep that in mind as we go forward with the rest of the notes. Either it's going to be an independent system which has exactly one solution, the lines cross at a single point. It will be inconsistent if it has no solution. That means the lines are parallel and they're never going to intersect each other. And then dependent whenever they have infinitely many solutions, when the lines are actually the same line. Now, one thing we want to keep in mind here is infinitely many solutions, that the phrase infinitely many solutions is not the same thing as all solutions. So keep those distinct. All solutions would mean any point in the plane is a solution to the system of equations, but that's not true. Only points that lie on the line are solutions to the equation. So as we write this down, we keep distinct. Infinitely many is not the same as all. Now, if we're given a graph, we could quickly visualize how many solutions there are, 1, 0, infinitely many, and where it would occur. But when we're not given a graph, we could still solve it through two different methods. One is called substitution, and one is called elimination. Let's begin by solving this with the substitution method. Now, looking at our system of equations, we have two equations in terms of x and y. And our goal is to find the solution. If there is a single point that's a solution, it would be sum x comma y. And the way that we're going to go about identifying whether it's one solution, no solution, or infinitely many solutions is by trying to solve for x and y separately. Now, in this case, for substitution, what you do is you rewrite one of the equations to get one of the variables isolated. And in terms of rewriting which one, it doesn't matter which you choose, but I think the first equation is a little bit easier to work with than the second equation in this case. So if I have negative x plus y equals negative 5 and I want to isolate one variable, I might work to get y by itself, which would mean that I would add x to both sides, and we would get y equals negative 5 plus x. So y is equal to negative 5 plus x. Once you've isolated that, you might box it so it'll be easy to find later on. And then in the other equation that you haven't manipulated, you now substitute that value in. So in the other equation, we had 2x minus 5y equals 1. We will now have 2x minus 5, but instead of writing y, we write what y is equal to in terms of x. And here's very important that since this has multiple terms, you write it in parentheses so that you could then distribute as needed later. So y takes on the value negative 5 plus x. All of that must be equal to 1 by the second equation. And now, once we've got replaced in the other equation, we now have something in a single variable. So we can simplify, group like terms, and solve for x. Let's do that. First, we would distribute the negative 5 to both terms. And we would get 2x minus a negative 5 times a negative 5 would be plus a 25. Negative 5 times x is a minus 5x. All of that equals 1. Now we had 2x's and then we subtracted 5x's. That would leave us with a negative 3x. Plus 25 equals 1, and here we begin to solve for x. So let's subtract a 25 from both sides. And we would get a negative 3x equals a negative 24. Divide both sides by negative 3. And we get x equals 8. Now once you found your first point, that's what takes the majority of the time. Then you would go back to the equation that we found earlier that rewrote x and y in terms of each other. So we know that x takes on the value positive 8. Let's find the remaining variable. We know that if x equals 8, then following this equation, y would have to be negative 5 plus 8, which is a positive 3. So we found the xy point, which means we could write our answer as the system of equations has a solution at 8, 3. So that would be our answer. And in this section, you'll always be able to check your work to know that you got the correct answer. The way we would go about checking our work is you would realize that we've listed this xy pair should be a solution to both equations. So we visualize this is our x term and this is the corresponding y term. And if this is truly a solution, then we should be able to substitute these values back into both the x and y coordinates of both equations and get true statements. So that's what we're going to do here. And it is important that you check both. So we'd have negative 8 plus 3. So plug 8 in for x, 3 in for y in the first equation. That is equal to negative 5. What did the equation say it was supposed to be equal to? Negative 5. That checks out. First equation gives a true statement. So the idea is when you substitute the x and y variables here, you should get what it's equal to on the right as well. Let's check the second equation. 2 times, now x is 8, minus 5 times y, y is 3. Now that's going to be 16 minus 15, that's 1. Let's see, what was it supposed to be? 1. Since these are the same, we know that this is truly the solution to the system of equations because the xy point makes both equations true. It's not enough to make one equation true, it has to make both. So through this, we verified that we did in fact get the right answer. Now the method we used here is called the substitution method because we solved for one variable and then we substituted that equation into the other. So that's why it's called the substitution method. Let's talk about another method to solve system of equations. This method is often called the addition or elimination method. And the goal here in the addition or elimination method is to, through multiplying one of the equations by a carefully chosen constant and then adding the two equations together, you are going to cancel one of the variables. Specifically, let's look here. We've got the system of equations 3x plus 5y equals negative 11, x minus 2y equals 11. Now, if I was just to add these as they stood, I would get 3x plus 1x is 4x, 5y minus 2y is 3y, negative 11 plus 11 equals 0. And this is not a particularly helpful addition because it still leaves an equation in two variables. The whole goal of the elimination method is to get down to an equation in one variable, because the thing you should keep in mind as you solve these problems is if you only have a single unknown, then you can use algebra to solve for it. The problem is whenever there's two unknowns in an equation. Okay, so that wasn't particularly helpful. It didn't get rid of the x or the y's. It did get rid of the constants. Why did the constants get removed? Because you had the positive and negative version of the same value. Plus 11 minus 11 goes to 0. So what we're going to do instead is we're going to say we'd have to manipulate one of the equations in order that whenever I add them, one of the terms cancel. Now one thing that I'd focus on here is, do we see this just has a singular x term? That's going to be easier to manipulate than trying to manipulate the y's, which are both like a 5y and a 2y or negative 2y. It's easier when one of the variables is already just 1 times x. Now I've got 3 x's up here. If I want the x's to cancel when I add the equations, then my goal would be to have a negative 3x. The only way I can get a negative 3x is if I multiply the equation by negative 3, but since it's an equation, what's done to one side must be done to the other. So I'd also have to take the negative 3 times 11. Now I'm going to distribute negative 3x plus positive 6y, because negative times negative is positive, equals negative 33. And that's our new equation. And what you'll do is then you'll rewrite the equation that you haven't manipulated, that you wanted to add to it under. And now we add these two equations. And as we were hopeful whenever we constructed this, negative 3x plus 3x cancels to give you 0x, which is just 0. 6y plus 5y would give us 11y. Negative 33 minus 11 would be negative 44. And this is something that we can work with because it's now in terms of a single variable. Now you can use the basic 4 operations of algebra to solve. 11 is currently being multiplied by y, so if we divide both sides by 11, we would get that y equals negative 4. Now, either with the addition, elimination method or the substitution method, once you get one of the values, then you'll be able to more quickly find the next value. So we have y equals negative 4. You can substitute this value of y into any equation that involves x and y, and then solve for the remaining x value. But since you can substitute into any of them, you might as well substitute into one of the ones that's easiest to work with. So in this case, I think the original second equation was easiest to work with because it had a singular x. So instead of y, I'm now going to put a negative 4 here. X minus 2 times y takes on the value negative 4 equals 11. Negative times negative would become x plus 8 equals 11. Subtract 8 from both sides, and we get that x should take on the value 3. Now this would give us the point 3 comma negative 4, which means the lines meet at one point as our solution. And as always, we can check our work. Now we're going to check the work the same as what we did in the last problem, so why don't you take a moment to pause the video right now and then check to verify if this is a correct solution by substituting for every y value negative 4, for every x value 3 in the original two equations. And then unpause when you're ready to check your work. So 3 times 3 plus 5 times negative 4, that would be 9 plus negative 20, which would be negative 11. What was it supposed to be? Let's look. Negative 11, that works out so far. Checking the second equation, 3 minus 2 times negative 4. Okay, minus a negative becomes a positive, so that's the same as 3 plus 8, which would be 11. Let's see, what was it supposed to be? It was supposed to be 11. We got what was expected. So it works in both equations. Therefore, we are confident that this is the solution to the system of equations. And for this method, it's characterized by finding a particular multiple that you can multiply one or both of the equations by, such that in the simplified equation, whenever you add it to the other one that you didn't manipulate, one of the variables cancel out, and you're left with an equation in one variable that you can solve. So the key thing for this method is that choice of a constant. You're trying to choose a constant so that whenever you add the two equations, one of the variables cancels. Now let's try to solve this method using the elimination method. So we're going to try to find a constant multiple where if we multiply one or both of the equations, then we subsequently add the two equations, we'll be able to cancel one of the variables. Now, particularly if I want to cancel the y's, there's many ways, many constants you can choose, so there's not just one way to do it. But particularly the reason I'm going to try to cancel the y's first is, do we see that they already are of opposite sign? One is positive, one is negative. Part of the work is done. Now we'd like to multiply by integers if we can, just because that does make the calculations easier. You could multiply by non-integers, but it would make things a little bit more complex. So there's no integer that we could multiply 3 by and get positive 10, which is the opposite of negative 10. So this is a case where sometimes you're going to manipulate both equations. You think, what's the smallest common value between 3 and negative 10? That would be negative 30 and positive 30. So what would we want to multiply the first equation by in order to get a 30y as part of the equation? And what would we want to multiply the second equation by in order to get a negative 30y as part of the equation? And of course the other terms as well, but the goal is to get the 30y and the negative 30y so the y's cancel. Take a moment to think about what constant multiples I should put here and here. We know 3 times 10 would be 30y, and then 3 times negative 10 would be negative 30. Now this 10 has to be multiplied to every term in the equation, both on the left and the right side. So 10 times 2x would be 20x. 10 times 3y would be 30y. 10 times negative 16 would be negative 160. So let's fill in our equation. Similarly, the 3 goes to every term on this equation. 3 times 5x is positive 15x. 3 times negative 10y is negative 30y. 3 times 30 is 90. We've manipulated both equations, but since we've done the same thing to the left and the right side, it's still the same equation. We haven't changed the value. So we would add the two equations, and as expected, the y's cancel because they're exactly opposite in value. 20x plus 15x would be 35x equals negative 70. And we're going to divide both sides by 35. That would give us x must be equal to negative 2. Now the majority of time in these problems is spent finding the first unknown value. Once we found that, the next value will come a bit faster. I'm going to ask that you would pause the video and find the value of y. Remember, we already know x has to be negative 2, so you can substitute that into any of the earlier equations and solve for y. So unpause to check your work. So I'm going to substitute into the first original equation. 2 times x takes on the value negative 2, plus 3 times the unknown value of y must equal negative 16. 2 times negative 2 is negative 4. And now I can solve for y. So I'm going to add 4 to both sides. That's the opposite of negative 4. y equals negative 12. Divide both sides by 3, and we would get that y should be equal to negative 4. Now that would give us the point negative 2 comma negative 4 if we wrote it as an xy pair, or x equals negative 2, y equals negative 4 set a separate way. Here we can check our work. So why don't you take a moment to pause the video now verify this is indeed a solution in both equations, and then unpause when you've completed that. So in the first equation, where there was an x, there's now a -2. Where there was a y, there's now a -4. That would give us 2 times -2 plus 3 times -4. That's -4 plus -12. That would be -16. What was it supposed to be? -16. That works out. Now in the next equation, everywhere there was an x, there's now a -2. Everywhere there was a y, there's now a -4. 5 times -2 minus 10 times -4. Minus a negative becomes a positive, so that would be the same as adding positive 40. -10 plus 40 is positive 30. What was it supposed to be? Positive 30. So that's a solution to this equation as well. Since it's a solution to both, we know that this is definitely the solution to the system of equations. So this is where the two lines would cross each other. Now, to this point, all the systems of equations that we solved had a single solution. But if you remember back to the beginning of this lesson, we saw there was actually 3 possible situations. The lines could cross at a single point, which we found those. They could be parallel, where there'd be no solution, or they could actually be the same line in disguise, in which case every point on the line is a solution, so there is infinitely many. So we've just seen this situation, but we are about to get to the point where we're going to see these 2 situations occur. Sometimes you can spot, based on how the lines are written, which situation you're in. For instance, if we had the systems of equations, which sometimes you'll also see these brackets in front of them to indicate that it's a system together. And they asked you how many solutions are there, we could instantly say no solutions, because since these are written in y equals mx plus b format, we can clearly see the slope for both is 5. Lines that have the same slope are parallel, so one of the lines would look like this, the other would look like this. Oops, sorry. Parallel lines will never intersect. So this has no solution. So if you're looking to see when 2 lines are parallel, you get them in the form y equals mx plus b, and you compare the coefficients in front of the x. If they're the same, they're parallel, which means there'd be no solution. How might you spot the opposite whenever there's infinitely many solutions? This next system of equations that I've written down are actually the same line in disguise. It might look like I've written 2 equations, but they're actually the same equation. Notice that the second equation looks like it's exactly twice the first. In fact, if I did multiply 2 times each term, I'd get a 2y, a 10x, and a 50. Whenever you recognize your system of equations, both equations are the same, it's just one is a constant multiple of the other, that's when you know you're looking at the same line graphed over itself, which would be infinitely many. So we would say here there's infinitely many solutions. And if it's not one of these 2 cases, then there's exactly one solution, and we've already seen in previous examples how to find that. Now, this is about to disappear as we work through our next problem, so if you'd like to copy it down, you might pause the video soon, copy it down, because it's about to be erased. Now, as we look at this system of equations, you can always solve it using substitution or elimination. The choice is up to you, but I would say it's good to be competent in both ways, because sometimes one is naturally a good choice for one problem versus the other. And I think in this equation, substitution is a great choice, because do we see we already have x is written in terms of the other side. It's already solved for x, which is the first step of substitution. So it'd be a good idea to now take this expression of x, 9 minus 2y, and replace it in the second equation. So why don't you pause the video and take that next step, unpause when you're finished, and we'll talk about the next step of the problem. So we have 9 minus 2y. That's what substitutes in for x. We were adding that to 2y equal to 13. Now, these parentheses, there's nothing that needs to be done here because it was just x by itself. And whenever we see this, we see that the y's would cancel. 2y minus 2y would be 0y, and we would be left with 9 equals 13. Now, we haven't made any mistakes. We followed the process, and as we followed the process, we get to a statement that doesn't make sense. 9 is not equal to 13. This is an untrue statement or false statement. And if you haven't made any mistakes and you get down to a false statement, what that means is that there's no solution. It means these lines are parallel. There's no point where they're going to be equal to each other. And that's the indication that you could look for otherwise if you don't notice they're parallel just by looking at their equations. So to recap this, as we go about the normal process of solving the system of equations, eventually you would get down to a statement that is just not true. 9 is not equal to 13. Once you get to this untrue statement, that immediately implies that there's no solution, because no solution can make this statement true. It's just never going to be true. Now for our next equation, I would say in the previous example, substitution made a lot of sense, but in this equation, do we agree that I could do maybe elimination? Since this is just a singular x here, I could multiply every side of the first equation by -3, and that would get my x's or my 3x and my -3x to cancel. So I'm going to say let's multiply this by 3. Remember that has to be distributed to each term, which would give us the new equation, -3x plus, I guess that would be minus 9y equals -6. We were going to add that to the second equation unchanged, so I rewrite it below, add them together, and as expected, the x's cancel, which was our goal. And then as we turn to add the y's, we also notice they unexpectedly cancel, -9y plus 9y. So that cancels as well. We weren't intending that, but that occurred because of how these equations are related to each other. And that leaves us with nothing left on the left side. Remember, nothing in terms of a number is 0. And then -6 plus 6 would also leave us with 0. And this is just a true statement. There's nothing that we can solve. We can't find the x or y value because there are no more x and y values. They canceled perfectly with each other. But as we're looking at 0 equals 0, we would say, well, this is a true statement. 0 is equal to 0. And what you're to take from that is that actually these are the same line. If you graph this on an xy plane, you'd get there the exact same line. So there's infinitely many solutions. And the way you can know that is as you go about the process of solving it, you get down to just an inherently true statement that doesn't depend on what the values of x and y are. It's just true for any x and y pair on that graph. So we would say there are infinitely many solutions to this equation. So as you're going through this process, if you solve and you get a distinct x and y point, check your work to make sure you got the correct answer like we've done in our previous examples, but that's when you'd visualize that the lines are intersecting exactly one point. If as you go through the procedure you get a false statement like 2 equals 3, what you should visualize there is that you've got parallel lines which never intersect, so the answer is no solution. But if as you go through your work you get a true statement like maybe 2 equals 2, that means the two lines that you are looking at are actually the same line, and they intersect at all points on the line, so there'd be infinitely many solutions. So you'll go through the same procedure each time, and you'll get 3 cases. You'll get either a single point, or you'll get a false statement, which means no solution, or you'll get a true statement, which means infinitely many solutions.